Okay, so you found some maps, but I think when you said this was one of the things that you thought was pretty interesting in the chapter, but the chapter didn't explain how you prove it.
Yeah, I think he just said that Cantor proved that these have the same size.
Yeah, this is one of the famous things because, first of all, I said this was surprising, so I kind of gave away that it's surprising. But why is this surprising?
Well, you have really infinitely many rational numbers that can fit in just the space from 1 to 2.
Right.
So you would think that that would create a larger infinity because you have infinitely many of these infinitely many rational numbers.
Yeah, just going from 1 to 2, just as you said, or even going from 0 to 1. Mm-hmm. I mean, obviously, they don't hit every number. Like, what's a number in between 1 and 2 that's not a rational number?
Square root of 2.
Square root of 2, which is about 1.4, so maybe there. That's missing. Somehow there's a hole there at square root of 2, but still, it almost looks like it fills in the whole line. In fact, there's a mathematical word for it, that the rational numbers are dense, which means there's actually no interval gaps. Any interval.
That's any interval's too large.
Yeah, any interval has infinitely many rational numbers in it, and no matter how small the interval is. So there's only holes, like single point holes. So it's a little surprising. So do you have any guesses at all how we might create a map from the positive integers, 2, 3, 4, 5, the counting numbers, to the rational numbers?
2, 3, 4, well...
We have to find a very clever way to count them, basically. Just to somehow say, like, this is, when I arrange them in a line, this is the first one, this is the second one. But I'm going to have to get creative on how to do that.
Well, I was thinking that you could start with ones with denominator 2,
Okay.
and then count and increase the denominator once you count all of them, but that only really works for the 0 to 1 interval. So, like, if you had the 0 to 1 interval, you count a half, and then 1/3, 2/3, and 1/4, and 3/4, and so on.
Oh, that's actually a very, very clever idea. You're right. Yeah, wow, this is a great idea. It does seem to have a problem that it only hits the ones in 0 to 1.
Yeah.
It does seem to have that problem. But if we can do that, let's first see if we can solve that problem. And then, what if we could make a map that went just to 0 to 1? And we showed that the rational numbers between 0 and 1, it doesn't really matter if you include them or not, because you can always add 1 or 2 points in, have the same infinity as 1, 2, 3, 4. How could we then, if we knew that, how could we then say, okay, that means all the positive rational numbers work?
Well, since that same infinity is in all of the gaps, you could say that adding on these gaps doesn't really change the size.
Okay, yeah, that's a little bit more of a hand-waving way, for sure. So it gives you some intuition that it would be true, but we can actually find a direct map that does it. And it's quite similar to one of the ones we looked at in the last video. So you're saying, I'm looking at the numbers 1/2, 1/3, 2/3, and then you're going to look at
1/4,
2/4, 3/4.
2/4 and a half would be the same.
Yeah, you've sort of double counted, but that's actually okay.
You could sort of have to, like, connect them up almost.
Yeah, well, we don't need to prove it. Just assume that we have this map.
Okay.
how can I extend the map that we have then to the positive, or the ones bigger than 1?
Well, somehow you'd have to, like, you'd almost have to go this way on the map. You could, like, not really sure.
Okay. What did I do with the even numbers?
You multiplied, like, you took the positive integers and multiplied them all by 2.
Okay. So so in some sense, I magically went from 1 number to 2 numbers somehow.
Yeah.
How can I do that here? How could I associate this fraction with 2 numbers? 1 below 1 and 1 above 1. And then associate this number with 1 number below 1 and 1 above 1. And then associate this number with 1 above 1 and 1 below 1. It's a very straightforward thing I can do. I already have the association below
Just
1.
add 1.
Adding 1 would do it, but it wouldn't give me all the numbers above 1, all the rationals. I need to find a unique number, rational number above 1 associated with this. A unique one associated with this, a unique one associated with this. And remember, all these numbers are less than 1.
Yes.
So what can I do to them to create another number above 1? Adding 1 works, but it doesn't give me, say, like 10.
You could somehow associate these numbers all with.
We're going to associate each one of these uniquely with a rational number bigger than 1. We definitely have the rational number less than 1 here.
Yes.
What's an obvious one we might want to try to associate this one with? 1/2 could be associated with
1. Like, 2. You could
2.
just take the reciprocal.
1/3 would then be associated with
3.
1/4 would be associated with
4.
2/3 would be associated with.
3/2.
Did I get all the rational numbers?
Yes.
Why?
Well, you take and, like, it just seems like you sort of fill in all of the gaps there.
Okay, if m over n is less than 1, then what happens with the reciprocal?
It becomes greater than 1.
Uh-huh. So I get them all in pairs. So once I have the numbers from 0 to 1, I can then uniquely pair them with the numbers from 1 to infinity. And I already know how to do the map that associates 1 to a pair.
Yep.
So that's going to show me that they have the same infinity. So now all I have to do is use your idea to get 0 to 1,
All right.
which was a great idea. All right, so let's try that now.